spring seminar series. And today, first talk is by Lucas Parra. I have the pleasure to introduce him. Lucas Parra got his PhD from München University, where he's been working on signal processing, mostly on the problem of separating sources and doing signal identification. He then he worked at Siemens, and he also worked at Sarnoff Corporation. Today, he'll tell us about adaptive signal processing, actually adaptive signal and image processing.
Well, Gert, thanks for inviting me. Good. I didn't know who was going to be here, and I thought I'm going to just be giving a talk to a few people that know about source separation, which is the topic of this talk. And so it's a very technical talk. Now I'm scared that all you people here probably don't know what I'm going to be talking about. But and I thought, gee, I should have brought some more fancy demos with audio, and I have none of that. Just a bunch of equations, bunch of ideas. So bear with me. So I'm going to talk about source separation, basically, in an acoustic environment. This is work that I have done with Chris Alvino, which is a very bright student that I have the pleasure to work with, and a bunch of other people in our group. I'm at Sarnoff Corporation, which is up in Princeton, and we have a small group that does some signal processing, adaptive image processing, different things. And we got interested in the source separation problem. I should put it differently. The customers here, Thomson Multimedia, got interested in some work we had done in the context of acoustic separation, meaning you're in a real room, there's noise, there's multiple sources of even the TV itself, for example, because Thomson does TVs, by the way. That's one of the many things they do, but they also do TVs. So if you're in a room and the TV is on, and then there's people talking, and then maybe baby crying, wash machine, whatever, everything is going on, and at the same time you want to maybe control your TV, right? So how are you going to do that? And at a distance on top of it, right? You don't want to walk around with a microphone here just to talk to a device, right? So they got interested in the source separation stuff, and funded some work in evaluating these techniques for actual applications. So much of the work that had been done in source separation was sort of with simulations, and people mix signals in their computer, and then they run some algorithm and it works great. But this talk is about, in practice, all of this stuff is nice, but it doesn't work with real signals and real recordings. And this talk is about why it doesn't work and how to make it work anyway. So basically, I'm going to be talking about combining some ideas that people have, because people have thought of this problem for a long time in the area of beamforming, right? It's not like nobody ever before thought of that problem. There's 20, 30, 40 years, I should say, of experience with how to get spatial selectivity with a bunch of microphones. So my effort was to combine some of these old ideas with some of that new work that has been done in the last 10 years on source separation. So this is what I'm going to talk about. What is source separation, and what are the criteria that people usually use to separate signals? And what the problems are. There's a number of ambiguities that make this thing in practice not work, I'm going to claim here. Then I'm going to say that using geometric information, such as people in beamforming do, will actually help us solve some of those problems. Then I'm going to say how this geometric information is included into the algorithms with making assumptions, basically, geometric assumptions on the response of the arrays and the filters. And then I'm going to give some examples of how to actually implement these ideas in actual practical algorithms. But when I first did this talk, I wasn't actually ready to give any results. So I structured the talk as, I'm going to tell you the idea, and then you take these ideas and go home and do it yourself, right? In the meantime, I have actually some results of my own, so that's good. So what is source separation? Convolutive source separation. The problem is this: imagine a bunch of microphones in a room anywhere, you don't know where actually, and a bunch of people, and every microphone records a mixture of all these sources. And not only the signal that arrives directly at the microphone, but in a real room you get also the reflections from the wall. In fact, if I'm talking here, we put a wall in front of you, right? You're still going to be able to hear me because you're hearing all the reflections. So actually, the indirect path is rather strong, and it's a serious issue in practice. So you cannot ignore it, and that's why we say this is convolutive source separation versus instantaneous source separation, where you just get the direct path basically, which is a much simpler problem, much simpler. So what we have is a bunch of sources here, say m of them, and a bunch of observations, x. So these are the microphones, these are the sources. And they are mixed together, this is what the sum over I is, and on top of it there's a convolution, so every signal maps from the source to the microphone with a whole sort of convolution, right? So basically the task is, I'm only given these signals x, and the task is, tell me what s is. And I don't know anything about a. So it's somehow a factorization problem, take a bunch of numbers and split them in two. So how are you going to do that? You need some information, right? So again, here I'm going to write it down how we're going to actually do it. We're going to take these signals x, the microphones, and filter them again with something that looks similar like that, and generate some model sources y that hopefully are as close as possible to these s. Simple, huh?
Are you assuming that m is known?
Yeah, let's assume m is known, right? Also, I'm assuming I have more microphones, or at least equally many, because if not, then you're trying to basically make up, from less observations, make up more explanations, which is always a difficult thing. You have to then put more assumptions in it. So, so just to rewrite this, if we write this as a matrix and this is a vector and this represents a convolution, this writes a little more compact, the same equation that we had before. If we convert this into the frequency domain, the convolution simplifies into a simple sort of multiplication. So here's a matrix. For every frequency, we'll have a product like this. So basically, I'm saying, given these x's, how can I factor this like that, right? And what I was saying before that, I'm going to filter this with a w, means that I want this y somehow to correspond to this s. With somehow, I mean they're not going to be exactly the same, because there's a number of ambiguities which I cannot really resolve. But somehow this w is supposed to invert this a, right? So what's the criteria people use? So I've told you, you have to take a bunch of numbers and split them in half, somehow explain as factors. And so you have to put in some knowledge, otherwise it's impossible to do. So the knowledge that you put in, turns out it's sufficient. Well, this talk is about it's not sufficient, but in principle people think that it's sufficient to assume that the sources are independent. So independence means, statistically independent. Means you're going to make assumptions about their moments, for example. You're going to say that the moments of these things factor. That's what independence means, right? Moments factor. So this could be true for any orders, could be for any set of pairs of these model sources, not being the same, of course, and for any delays. So a delayed version of the signal is still going to be independent. And in fact, if the signals are non-stationary, this should be for all times the case, right? So basically, for any t, for any tau n or m, and j not equals to j, I'm gonna ask for these model signals to have this property. And it turns out that some people have shown a few things about this criteria. It turns out that you need, in a convolutive case, you need this multiple taus basically for the filter taps. For every filter tap you need one of these taus. So you have to assume this for a bunch of these taus. To get separation, people have shown that you have to have that just correlation, meaning n equals 1 and m equals 1, is not sufficient. So just decorrelating signals is not sufficient. If, and that's a thing, if you consider the signals are stationary, so basically you ignore the fact that the signals change maybe over time. However, it turns out that if you use higher orders, higher order moments, a bunch of them, or a selected set that you know is important for the signal, this criteria is sufficient to actually identify these W's that I mentioned to you before. And also it's sufficient to use second order, meaning n and m equals 1, if you know that the signals are non-stationary. Basically, you're decorrelating the signal at one time, but at a later time and at a later time. And the filter that decorrelates them at all times is the one that actually separates. So there's some stuff that proves all of this. And this talk is going to be about problems with this criteria. So I transferred this problem into the frequency domain basically because when you have these long filters in a real room, you need about filters of like 1,000 taps or even longer. If you have these long convolutions, you need to get like some efficient algorithms. The usual way how to do that is by taking things into the frequency domain. And so people have suggested take the criteria as well into the frequency domain. So if the signals are independent, their frequency representation is also independent. I mean, the moments will also factor, right? And using this criteria, you can derive an algorithm which we've published, done 3 years ago, published this year. Yes?
You have to limitation there. What's YIT omega? What's the T?
Oh, sorry. I'm still assuming that the signals are non-stationary. So if you take a certain window and do frequency analysis at that time, you'll get something else and you do it later. And when I'm saying estimate, I mean some sort of estimate around a certain time, which is a hard thing to do anyway. What does it mean if the signal is non-stationary? But some notion of at a time, right? Statistic at some time. So anyway, if you use this criteria, you can derive an algorithm that is rather efficient because it's done in the frequency domain. It can actually run on real time on some not too complicated hardware. You can use only second order statistics, which is good because higher order moments are always hard to estimate and makes your algorithm sometimes unstable, or you have to make assumptions that aren't really always valid about the statistics of the signal. And it basically results in an algorithm that is sort of cross-power minimization, or across time. So that's all good, and that's the algorithm we started with when these people gave us the money to see if it actually works, right? And but there's some problems with this criteria. In particular in the frequency domain, and that is, I said that this W is supposed to somehow invert this A. So what you're saying is that up to permutations, right, when you can always flip which signal you call 1 and which one you call 2 and 3 and 4, right, up to permutation, which is this P, you don't know what the inverse will be. And in fact also up to scaling, so this P and D, so this was the permutation. So up to permutation, we don't exactly know what that inversion is going to be, right? And also the scaling, scaled signal is still independent, right? If I multiply it by 2, it's still independent from the other signal, right? And if you use, in fact, even more microphones than sources, it turns out there is a whole linear subspace of solutions W that will invert this A, right? So there's a number of ambiguities that independence criteria does not specify, right? Scaled versions are always independent, permuted versions still independent, and just by simple linear algebra, there's a whole n minus m dimensional, n being the number of sensors, m being the number of sources, dimensional subspace of solutions to this.
Yes, are those ambiguities also there when you use moments rather than?
Yes, this is just generic. I mean, as you said, you notice maybe in my choice of words, I always said signals are independent. When you scale them, they're still independent. Independence means in all higher or moments.
Well, I mean, you have two different criteria for defining independence. One was using higher order moments,
right?
And the other one was independence of different instances in time. So if you use the higher order moments formulation, you still have this.
Yes. I mean, if something is going on that is independent of that, it doesn't matter what moments you're measuring, it's independent, right? And when you scale it, it's still independent, regardless of whether you measure second order or third or measure second order at different times. If you say the signals are independent, no matter what metric you have of independence, this is an ambiguity that is principal.
But if you use higher order moments, then you get sums and differences of frequencies.
So In the frequency domain, this criteria, as I have written it before, basically for every frequency bin, this is a totally separate problem, and you still have that. Now, when you measure things in the time domain, it might be, and that's, I'm going to get into that. But in principle, I'm arguing that all these three things, no matter what criteria you have, that's the case. But it's, you know, it's well known. It's not something that people haven't bothered too much. They say, well, if you implement this in the frequency domain, you have to sort out the permutations somehow, right? They knew that. And this dimensionality problem, well, you know, mostly people don't consider using more microphones than sources. And the scaling, well, yeah, we know that the signals will end up being convolved somehow. The point is that if for every frequency bin you have a different scaling, it means that you can sort of convolve the signal, and a convolved version of a signal is still independent from another signal, right? To that one thing, you can do whatever you want. It's still going to be independent from others in the first place, right?
What is permutation in the frequency?
I guess what I was saying is that the criteria that I had before, it's when you transform the problem into the frequency domain, you basically have for every frequency bin, you have a separate problem. For every frequency, you have this factorization problem. So now you can choose, you know, for this frequency bin, I'm going to assign this signal to channel 1, this signal to channel 2, and the other to channel 3.
The frequency domain criteria were sufficient, were necessary but not sufficient for independence of the signals themselves.
Right.
So you not used all the power that assuming independence of the signals give, and that's why you end up with frequency bins, the permutation problem.
No, I think you are using all the information.
Isn't it true that you could find a signal, a pair of signals that satisfied your frequency domain criteria, but were not independent?
Right. In the time domain, right.
That's a
right.
problem.
In so that's what people traditionally thought. Oh, this is just an artifact of you taking the problem into the frequency domain. You make them independent problems, and now you don't know how to sort it out. Just remain in the time domain, regardless of how complicated that is in practice to implement these algorithms with long filters in the time domain. That's what conventionally is thought. If you go out and talk to anybody that's worked on this problem, they'll tell you that. Oh no, but just stay in the time domain, you'll be fine. I'll show you that's not the case. And that's exactly what this slide is. So right, if we're in the frequency domain, no matter what order we're using, we have this, at every frequency bin, a different problem, and therefore the permutations could be like randomly assigned, and obviously once you put the signal back together, you get something that is mixed up. But I'm going to argue here in experiments that also in the time domain criteria you have a problem. So I did a little experiment, right? Here's this spectrogram of somebody speaking, and here's some music, somebody singing or something. I don't remember what the signal was, but it's speech and music. And I took a bunch of bands and flipped them. I took them from here and put them here and the other way around, right? So basically simulating this permutation issue that once I put the signal back together, I wasn't sure which belonged to what, right? And if you do that and measure this time domain criteria that I mentioned to you before, in all possible orders. So you measure, you know, this product from its factorization, how far is it apart, right? And ask yourself, if I do this little game, what happened to that criteria? Is this criteria robust to this sort of thing? I mean, does this become less factorized here if I do that? And the answer is no, this criteria is actually blind. Here, what you see going in this axis is the percentage of bins that I have permuted wrongly. 0 means they're all correct permuted. 50% means they're all, you know, half-half, right? Half is correct, half is not correct. What you see here, this is for the correlation criteria. So N and M, basically the lowest order, second order, third order, and fourth order criteria. In the fourth order criteria, you see that these are down here the diagonal terms, meaning I not equals to J, right? So basically, as the permutations, when the permutations are correct, you get this to be the lowest, which is so the distance of this is well factored, right? The distance is smaller, and as the permutations increases, this goes up. So this would be correct. This would be saying yeah, as the permutations are wrong, this thing in fact does measure that. It does realize, oh no, now you're mixing them back together. This is for speech and speech. I just took 2 signals. This is for another signal that I took, speech and music. So you see already there's a little kink here. This, you know, here the minimum would be like a 10% permutation. So for these 2 signals, this metric, at least for 4th order, this one is still correct. 3rd order, the 2nd order is actually totally independent to that, would already start to have a problem. And these signals are, I think, 2 music signals. Now here, this is totally the other way around. For these 2 specific signals, it comes out that you get this to be best factored, basically. Empirically, this is always an empiric metric, right? If they're totally permuted, like the bins put together like this, right? So this criteria, okay, I haven't checked all orders, that's correct. Somebody could argue, well, you have just checked 2nd, 3rd, and 4th order. Well, you know, whatever, I bet you if you go higher up or some combination. Basically what I'm arguing here, this is not a robust criteria, even in the time domain, so I think that answers your question, right? So, and this is empirical evidence. Clearly the criteria is dependent, it depends on the permutations, but it's not a consistent metric. That's what I'm trying to say here. If for any given 2 signals, you might end up that this doesn't actually do the right thing. So I'm going to argue that that maybe you can use geometry to solve some of that problem. And before I go into that, let me say how I'm going to talk about geometry. And I'm going to look at the response of an array. So if I know where the microphones are, I can actually start thinking about, all right, if the array is here, you know, a bunch of microphones like that, what is the response in this direction, or what's the response in that direction? And that's this quantity here. So if these are the filters, this is the response in a particular angle at a particular frequency. And this D is something that specifies the array. It's something that has to do with the dimensions of the array, the positions of the here's the positions, the microphones, the angles, the frequencies, sampling frequencies, stuff like that, right? So by looking at this R, I'm going to be able to say a specific filter, what spatial, you know, response am I getting? So here's some results that we had at the beginning of this project. This is the case where we tried to separate 2 sources and had 2 microphones, and just ran the algorithm, and we get pretty good separation. We get 15 dB and 18 dB. Signal to interference ratio, basically from 0 dB where both were equally loud, right? We went to 15 and 18 dB in one channel and the other, right? So there's a serious crosstalk reduction there. And you see what the algorithm did, it placed a 0 here at angle 0, and then for the other channel it placed a 0 at angle something like 45 degrees or so, minus 45 degrees. So it kind of did the right thing, right? There's something funny going on here, who knows what that is, right? If we take the same array configuration, I think the only thing we varied here was that 30 centimeters aperture. We changed the aperture, we made it bigger. So if you increase the aperture, you would think actually that you get better spatial selectivity. So there's no reason why the algorithm should work less well. And it turns out that here we get just 1 dB improvement, here like about 3.6, so like didn't work basically. And what we see is, I think, if you look down here, what happened is that this portion of the array was listening here, was placing a 0 here, and here, and the other was placing maybe a 0 here. So and here we got something consistent. So basically, just at certain frequencies, so across here, I'm sorry, this is the frequencies. I think you noticed that already, right? For different frequency bins, this is sort of like messed up, right? It didn't assign them correctly. And we're able to make that judgment by looking at the geometry, basically, of the response, right? So already here is an indication that geometry is going to help. So I said also there's this problem with the you have more microphones than actual sources, so there's a sort of a whole linear subspace of possible solutions. You know, ask anybody that knows a little bit about signal processing. What do usually? You find some subspace method, right? You take your data, apply some, like, what is it called, principal component or subspace analysis, whatever you want to call it, and recover the subspace where the sources or the signal is actually living. And if you do that and look at the resulting filters, you'll see that the first principal component, the sort of the direction of maximum power, for a bunch of frequencies, again, here's frequency, here's angle. For a bunch of frequencies, it thought the strongest one was at angle 0. And for another set of frequencies, it found that the strongest is at another angle. This is the same data as before, right? So you see, again, we get this mess up of, like, what gets assigned to what, right? And again, oh, by the way, the third also contains a little bit of the power that was here at angle 0. So this method is like a bit of a problem, right? But again, we're able to make this judgment by looking at the geometry, right? At what the response is. So maybe we can use that actually to fix things up a bit. So the problem, maybe you know that already, is that subspace analysis will give you orthogonal filters, and orthogonality geometrically means nothing. I mean, filters where the coefficients are orthogonal to each other means geometric, in the actual space in a room means nothing, right? So that's why this is maybe not such a useful thing to do. But at least it helps you think about this geometry issue. So my first conclusion is that if you look at the geometry of the response, maybe you can sort out some of these problems. The subspace problem, the problem with the ambiguity in permutations, maybe not scaling. And so then we ask ourselves, so how does geometry get included usually in regular or traditional beamforming algorithms, right? What people do usually, sometimes there, for example, in an algorithm that is called linearly constrained minimum variance, is to say, I know my user is here, so I'm going to enforce that I get a constant response in this direction. Other than that, I'm going to minimize power. So everything that is coming from other directions is going to get minimized. I'm going to place a 0 for wherever the interference are coming from. But here where my user is, I'm going to get constant power. That is enforced by a simple linear constraint where you say that the filter times the array vector is constant. So while you do your power optimization, you enforce this linear constraint. It's a very simple thing to do, to enforce a linear constraint in an algorithm, right? There are some algorithms that they're called robust beamforming, that say, well, not only I'm going to enforce a constant result there, I'm also going to say it should be smooth, like right next to it. It shouldn't like go down or something. It should be sort of smooth. So the derivative with respect to the angle should be 0, right? So not only I'm going to listen in this direction, I'm going to also around it kind of listen in that direction and not place zeros right next to the user. So that's another linear constraint on the filters. Another linear constraint that is applied in multiple side lobe canceling is to say, because if you minimize power, the thing that minimizes power best is to set the filters all to 0. So obviously you cannot do that, right? So you keep somehow the power or the scale constant by enforcing a simple constraint like this, where you say one microphone I'm going to keep constant and just subtract from it, right? So you see all these different things these beamforming people use are oftentimes just simple linear constraints, and that's how you can include geometry. Well, that's simple enough. In fact, with this linear constraints, if you combine them, a bunch of them, you can like shape filters in all kinds of ways, right? Here, for example, we had 2 microphones and insisted with a linear constraint that there'll be a 0 at this angle, 0. Or here we insisted there'll be a minimum or a 0 here, but while keeping the rest as constant as possible for a bunch of angles. Or here we insisted to have a 1 here and a 0 there. So you can shape beams in all kinds of ways with simple linear constraints. So I'm going to combine that with my source separation thing, right? Now I learned how you do geometric information, how you're going to combine it. Well, if you remember what I said before, in the source separation, so let me first say what I have here in the first line. What I'm writing here is what the power of the small sources is, or the cross powers, I should say, in terms of the microphone cross powers, right? Just sandwich with the filters here, basically. It's a very simple square expression of So this is what I observe, and this is my model, right? In the source separation, as I had explained before, I said you should diagonalize this thing at multiple times. So this is the expression here. The off-diagonal elements of this thing should be minimized. I should find the filter that minimizes that, some expression like that, right? In beamforming, people usually look at powers rather than cross powers. Just sort of simple minimize power while enforcing some other constraint. And it looks very similar, right? This is like the diagonal terms of this thing. Minimize that. Well, these expressions look so similar. It's almost straightforward now how to do it, right? So this is the second conclusion. The way how to do it, I think, is use the linear constraints from geometric beamforming and the cross power minimization criteria from the source separation algorithms, put them together and see what you get. And here's the point where we could stop and you go home and then like implement a little something and publish a paper, right? And then acknowledge me somewhere. But of course I had to try this myself, and I had also some time. So basically there's a whole bunch of questions once you start designing algorithms, is like which geometric constraints, where are you going to get the angles from, so what localization algorithm you're going to use, what optimization, how you're going to do this in online, and all those sort of questions. And this is algorithm design. You could answer this question in many different ways. You come up with a slightly different algorithm, maybe a new paper even. So I tried two different things. The one is to take that diagonalization criteria that I have mentioned before across multiple times. So basically this is an existing algorithm that's been published. And then constrain them linearly, as I mentioned before, to give a constant response at a specific angle that I find with some like angle finding algorithm or something. Or even simpler than that, I realized if you just initialize the filters properly, they'll converge to the right permutations, for example. So here, a lot of results. So what is all of this? Can you tell what the uses were, by the way? But have you looked at enough of these things? No? Well, here's one, and here's the other, right? And these algorithms have tried to place a 0 here while keeping a constant response here, for example. And in the other one, in the other channel, keep a constant response here while placing a 0 there, right? And so this is a case where we have 8 microphones here, 4 microphones. All that mess you see there is basically spatial aliasing, because you don't have enough microphones, and so you get all these spurious side lobes, right? As you have more and more microphones, you can better shape like a main beam and then place zeros everywhere else, right? What else can I say? Oh, the other thing is about these algorithms. You see what this funny stuff happening along this line? This is where a 0 is crossing a grading lobe. So basically what happens at this specific frequency is the problem is not invertible. So the forward model, the thing that mixed it, is not invertible. Basically, if you're listening into this direction, you will also automatically be listening into that direction. And if your user happens to sit in that direction, you have a problem, right? You can't separate them. So in these locations, you get like issues like that. The forward thing is not invertible, and the question is, how do you deal in an algorithm where you're trying to invert something that is not invertible? So you have to start doing like, instead of enforcing strong constraints, you enforce soft constraints and then penalty terms and stuff like that, right? So so if you do that better, you'll get better results, and that's where all that tweaking comes in that you do when you do algorithm development, right? And so these are dispositions in here. So basically, it's hard to say what, this works kind of okay, but how does this work compared to another algorithm, this and that? Let's just, what is this one? I wanted to show the performance comparison. Let me just add to this one. Here, what you have here is just regular delay sum beamforming. These are the corresponding beam patterns. So the performance these things get is very poor compared to the other ones, which are around 10 to 20 dB. Here we get just like 3 to 5. something very poor, because it's not data adaptive. You're just using the geometric information here. And this is just to compare how these algorithms stack up. This is when you just let it go and initialize it with that. And now we come to the performance comparison. So I did extensive simulation, well, actually not simulations, real experiments in a room much smaller than this. You see here the dimensions of the room with 2 users, 8 microphones. I used different number of microphones. There's actually an experiment also with 3 users, which is actually so far never been published. I don't know if anybody doing in a real room with three sources actually getting separation. And I claim that's because of this permutation issue, because as the number of sources increases, it's a combinatoric problem of possible permutations, right? So I think that's why you haven't seen anything in the literature yet. So I vary this angle, and what else do I vary? The number of microphones, and I get a whole bunch of numbers. So every box is a different algorithm. Red is like dark red is 18 dB, down here is 0 dB. So this works the best, right? It's around, the average performance. Oh, this axis is number of microphones. This is 2 microphones, 4, 6, 8. This axis is angle of the users. If they come very close together, you cannot resolve them. If you go further apart, you can resolve them somewhat better. So this is angle, and this is number of microphones. And these are different algorithms. The first row here are the Laysan beamformer, what is this? Linearly constrained minimum variance, and this one I forget. It's beamforming algorithms. So what you can see is that this works better than that. That's the main message of this slide, right? So these algorithms I'm proposing here that combine geometry and source separation work better than just geometric algorithms. And which instance of which is like what, you look it up in the paper. But basically, that's the main message here.
How much of a slowdown is there by adding more microphones to the processing?
Well, if you have always a constant number of sources, then it's a linear increase in everything, in memory, computing power. If you increase the number of sources, then it's a square increase, right? Together with the number of microphones. Basically, I can run right now 16 microphones and 3 or 4 sources in real time on a fast PC. Or probably more even, actually. I haven't measured it. Right now it runs on 10% of the CPU time. The reason why this is so fast is because it's all in the frequency domain and everything is right. Yeah. So that was the important criteria, design criteria. And this is the results I'm getting for separating 3 sources. So as I mentioned before, I don't know if anybody's published that yet, that you can actually do it. And what you see here is from the Laysan beamforming, this is 2 dB up to 14 dB. This is average performance in a number of positions where I had 3 sources. There's only if you only have angle as a resolution, there's not so many possibilities how to place them, right? Closer, further apart. A number. It's not too extensive simulations. This is like 3 or 4 different scenarios with 3 sources. So here's the Laysan beamformer. This is linearly constrained minimum variance. And up here, this is what works really well. This is cheating. This is when you actually have additional information, when you actually know when the users are quiet and when they are talking. Because when they are quiet, you know that everything you're hearing is noise. So you can minimize the hell out of it. So that's really simple. So this is just sort of given as a benchmark to see how well can you do if you have sort of perfect information in this configuration with this microphones, right? And these are different versions of the ideas that I mentioned before. Basically, the one that works the best is the regular source separation, where you have just initialized the thing to sort of delay some beamforming and then just let it go to minimize cross powers. The problem with this algorithm is if you just let it go at these frequencies that I mentioned to you where it's ambiguous, you don't know what to do, it'll just zero everything out. And so if those frequencies are important, say for recognition, it just happens to be at the frequencies where you recognize actually has some important features, it's going to zero it out and they're gone and you can't have a recognizer run on it. So all of these numbers are in terms of SNR, but if you need this for a recognizer, you'll find out pretty soon that SNR doesn't mean a whole lot. That's the latest status of this project, is that you really need to look at the recognizer in terms of enhancement, and not SNR means nothing really. So yeah, so the main message is my algorithm works best. That's what these things are always supposed to show, right?
Were these experiments done where the three talkers were static?
Yeah, this is
So
static.
you haven't tried anything where the talkers actually move around?
Right. In the past, I have done simulations of an online version of this type of things, but not with these geometric ideas yet. I haven't put things all together. I get that you need about a second or so of signal. So if I'm like probably tracking and walking like this fast, it might be okay, right? But if I turn around like that, that's going to be a problem.
Actually, something was not clear to me. Do you assume that the speakers are the positions of the speakers are known, or they also find it?
I assume that the position of the microphones is known, because that's the only way I can generate some. That's fair. And then the positions of the speakers, turns out that if you have a lot of microphones, it's not so hard. It's not, in a practical application with a lot of stuff going on, it's not easy either. I'm not going to say that, but it's not too hard. All of these results were obtained automatically without giving it the position. It just found it. I used some music type algorithm basically. Just straight off to, some literature, look it up, do it. Yeah, so yes. So I think that the main thing here why this works is because I'm assuming that if the user, and this is the main assumption in here, is if the user is there for 1 kilohertz, he's going to still be there for 2 kilohertz and 3 and 4 and 8, right? That's the main assumption, I think. And that it's well localized. If it's diffuse, this is not going to work because you can't say where is it. It's just diffuse noise coming from everywhere. So then this is also not going to work.
So this is not multipath. This is not multipath. You don't assume reflections.
It is so right. So the constraints, the geometry is put in as making a far field, reverberation-free environment. That's how the geometry gets put in. But the adaptive algorithm assumes multipath. So that's if you just assume geometry and don't do any adaptation to it. And the adaptation that assumes multipath is what brings you up there. So in summary, I said that source separation has a number of ambiguities that lead to practical problems and lack of robustness of the algorithm. Works sometimes and sometimes it doesn't. And I would really encourage you, if you start reading papers on this stuff, start in the back and look at what experiments they do. If they did any experiments in a real actual room. And if they do that, then go to the front and start reading the paper. Otherwise, put it aside, because there's so many papers that I think if they're claiming convolutive separation, if they're doing something else, fine. But if they're claiming convolutive separation, just read the experiment section first and then go to the front, right? Anyway, so there's a number of ambiguities that lead to this sort of practical problems. And one solution I give here that is, I think, rather generic is use geometric information, like you know where the microphones are, can make assumptions like the user's localized. If it's fair. If it's not fair, then it's not a good assumption. Don't do it, right? And I've more specifically said that you could do it by doing cross-power minimization combined with the linear constraints that you take from geometric beamforming. And And I'm saying that this is a rather general approach because you could have also used higher order criteria. It doesn't need to be cross power. It could be any of the other sort of algorithms that people have proposed for convolutive separation. And you could have used other sort of geometric assumptions, maybe not linear stuff, whatever you pull out of the beamforming literature that sort of fits in this scheme. So I think it's a very sort of general idea, and there's a number of algorithms that could be fit into this sort of general framework. Thank you for your attention. Any questions?
More questions?
So you said that signal to noise ratio wasn't as important, which actually helped to recognize what kind of recognition experiments?
Dragon and IBM Via Voice, continuous dictation as well as command and control with trained engines.
So you would actually train people in this environment, so standing some distance from the television?
No, well, we actually trained it on close by speech. So a microphone placed here. The assumption there is, I guess, that if you train at a distance, what distance and where exactly, and so as a reference, we took actually the same microphones, but close.
So what happens to performance?
If what?
Well, so how does it compare when somebody is standing far away from the TV as opposed to when they have the microphone?
Right, so if it's quiet and you don't do anything with the signal and you have cardioid microphones, which is what I used here, you can go away from the and it's quiet room, right? Then you can go away and you'll be fine for a long time. But as soon as you start fiddling with the signal and doing this sort of this processing and by accident sort of deleting a few bands and this sort of thing, it goes down. So reverberation, whenever you hear it and you say, "Well, man, this sounds like through a tube," then the recognizer will also complain. And sometimes you hear signals that say, looks fine to me, right? Sounds really good. I mean, I think this is really better. It's less interference, less, TV signal, whatever in it. But you put it through the recognizer, and the recognizer likes the original better. So that's if your application is really recognition, I think we have to start thinking about, okay, what should we optimize? Not powers, maybe. Maybe that's not the right thing to optimize. Maybe we have to find something that is closer to the engine. And in general, in the single channel enhancement, it's been also my experience. There it's all kind of obvious, right? If you have a single channel, the only thing you can do is mess up the signal in some way. And you just hope that you mess up the part that corresponds to the noise and not the one that carries the feature vector. So there people know that it's a trade-off between enhancement and distortion, obviously, right? And there the notion is that if you want to use this for recognition, you have to do this kind of together. In fact, to the point that people that do speech recognition actually don't like any kind of enhancement because they find that just messes up things. They know how to do it better anyway, right? So don't touch the signal even. And what I'm saying here in the multi-channel thing, we have some ideas how to do cancellation without altering the signal too much, but I think we'll find out soon for practical applications that you'll have to merge that enhancement also closer with the recognition. Like, for example, not use power as a criteria, but something else, which, you tell me, I don't know.
Questions? I have one. So how would you extend this then to the case where you have reverberation in the environment? And you can't use classical beamforming, or you can't use the angles of interference and sources.
How would I extend it? I think what you're asking is if the room is so, because I'm using it right now in a reverberant room, like right now. These results are real recordings in a real reverberant room. What would I do if this initial geometric assumption is so bad that it doesn't even help to guide the thing right? I would think about something different, I guess. But it turns out that sort of simplistic, reverberation-free, far-field assumption is fair enough to at least, kick sort of the source separation algorithm to do kind of the right thing, and then I think that's the basic idea. There's other ideas what to do if you can't use geometry, but I'm not going to tell you right now. No, basically you have to look at more statistics of the signal. That's the basic idea. If you have to start exploiting how different frequency bands are correlated. Because when we speak, when we're quiet, then the power is gone across the entire spectrum. And when we're saying something, it comes up everywhere. And that statistical information is something that needs to be exploited to sort this out without resorting to any geometry.
Okay, thank you, speaker.